Thank you, and thank you very much. I'm excited to be here today and talk to you all about some of the advances that we've been making in quantum. And my role has changed since I even submitted this. So I was the Senior Research Manager for Quantum Computational Science, and this is my new title. So I'm now the Technical Program Director for Algorithms and Partnerships for IBM Quantum. Long history in IBM research as a whole. I was just reflecting, I've actually been involved in quantum now for 8 years, which is mind-blowing to me. I come from a background in chemistry, a PhD in chemistry, and have been involved in some of the leadership tracks for the last 6 years. And I can only underscore that we have some of the absolute best people that we work with on a day-to-day basis. And so I feel very fortunate for that. Wanted to spend some time today, so as some of you may know, and some of you may have also come from, our Quantum Summit happened this week as well. So we overlapped with Q2B. So on Monday, we actually had that was our big kickoff day. And so we made a series of some announcements on Monday. And so I figured, like, for today's talk, it'd be great to share what we talked about there with you all. And certainly, I am more than happy if we have time at the end to have a dialogue about any of what you see and answer questions on it. So that's sort of my approach. Again, this will be at least like a little bit through my lens and where I'm coming from in terms of how we actually use quantum computers and what we see as being useful for the next decade, essentially, of quantum computing. So here are some of the highlights from the Quantum Summit. It boils down to, and there were more, but this is kind of the distilled list, if you will. I also included in my slides like the YouTube links for any of these. So if you want to go and actually watch the session and get like a much deeper dive on any of these, I would highly suggest that you do that. But basically, what it comes down to is we announced, that we are in the era of utility, and I'll talk a little bit about, like, again, what that means, and sort of from my perspective as well. We announced 2 new IBM quantum processors, so Condor and Heron, and I'll chat a little bit about what that entails. We unveiled our design for Quantum System 2. So this is our next generation of quantum systems. And then in the software front, we announced that we are actually releasing Qiskit 1.0. So that's a really big change for us. And then in addition to that, we've brought some AI to different parts of workflows to quantum. And then finally, and this is one of the, I think, biggest changes for us, is that we have expanded our quantum roadmap. So I'll share with you some of that as well. So the era of quantum utility, and what does this mean? So this is this data is based on a paper that was put up on arXiv. The first version of it hit arXiv in July of this year. And it was a really interesting kind of comparison across all the different quantum processors and what type of research was going out and what scale and size people were looking at when they were running experiments. And what you can actually see, so there's some dotted lines that show essentially the power of different computers. In fact, an IBM PC from 1981 is shown on here. And you can see that if you were to follow this trajectory, a lot of the literature is on 20 or fewer qubits. And if you were to like plot that out, then essentially what you're saying is that we're not going to be able to get to 100+ qubit experiments until like 2038 or something like that. And so that is obviously far, far, far too long, especially since we have made available and have available 127 qubit Eagle devices. And then last year at Summit, we announced our 433 qubit Osprey device. So this is a little bit, far too long for what we're actually developing in terms of the actual hardware. So if you wanted to check out the arXiv link, it's right there. You can actually go and read the paper. But essentially what we realized at this point is like, okay, if we can't follow this trajectory, we need something that's more representative of a disruptive change in how we manage quantum computation and unlock the potential of it. And so one point that we really think shows us inklings of this disruptive change is in this paper that we published this year. And so among ourselves, we refer to this as the utility paper. And basically in this paper, again, if you haven't read it yet, I highly suggest you do. It made the cover of Nature, something we're very proud of. It basically was a 127 by 60 qubit experiment that we were able to run for an Ising model. So this is, essentially a condensed matter physics example where we really show that you can start pushing the scalability of different circuits that you can run, as well as the depths that you need to run this. And then in addition to that, something that really set this paper apart is that there was a certain number of experiments in the regime that they were looking at that you really couldn't access without applying approximate classical methods. So there was no classical exact solution that was possible for a certain number of data points within that regime. And we have a very high probability in the particular instance where we're using error mitigation that we are extracting noise-free observables for that regime. And so it's just interesting because what this really means, and again, putting my lens on this, right, is that quantum computers are now becoming more of a tool that is something that you can use as a part of a toolkit. So you have your classical methods and approximate methods that you can calculate that way. But then you also have this other kind of data set that you can derive from running experiments on a quantum computer. And so this puts us into a little bit of a new era where we don't have an exact answer necessarily, classical answer that we can compare to. When I think about this a little bit in terms, and again, like with my background being chemistry, this isn't necessarily anything new to the field of computational science. In many ways, what we do when we set out to run any type of calculation is you're looking for the highest probability answer that makes the most sense and that actually matches something that you observe in nature. And so what that's really saying is that we're entering into an era where we're seeing the very beginnings of this in certain very narrow examples, which over time will accumulate iteratively, and we'll see more and more examples of these that we can then apply to problems that are of interest to various fields, right, and domains. So this was really a breakthrough in terms of the number of qubits. You now see, essentially this disruption, right? This curve now changes, and now you have examples of well over 100 qubits in terms of different experiments that we can run on the hardware. So we refer to these examples, and there have been a handful to date as utility scale experiments. And you can see that with the purple hexagon right on the chart. So we do think that there's going to be more of these that come up. So there have been a multitude in the last 6 months that we've taken notice of. Some of these are our own research. Some of these are done independent of IBM, but certainly involve partnerships that are incredibly valuable to being able to actually accomplish this scale of experiments. And again, this YouTube link here at the bottom, if you go and check it out, there is even more work that they highlighted at the summit that really kind of show directions towards these larger scale experiments. And if you watch Jay Gambetta in his opening talk, he makes the point that if you're not working at 100 plus qubits, you're not doing quantum. And so that's a very strong statement that he's making at that point. But what he's essentially saying is that you're not using it in a way that you actually have a sort of utility approach to the problem or some sort of answer that you're getting out of the quantum computer that you wouldn't otherwise have any chance of getting out of a classical computer. So that's what he's referring to when he says that. But I think, putting this into context too, you can see there's a lot of different topics that are shown here, and we're starting to see ones that actually have applicability in some areas such as high energy physics, for example, and then materials science. And so it's starting to move from sort of proof of concept, I would say, experiments to ones that have at least, a flavor of practicality and something that you would actually see being used to study a problem in these different areas. And so that is another thing that, again, from my perspective, is an incredibly exciting turning point in this. The other thing that I think is worth mentioning is you can see on here the gate counts for each of these, and they vary all across the board depending on the different problems that you're looking at. But I probably don't need to tell anyone who's tried studying any problem of interest with a quantum computer that gate count is very important, and that quality of the qubits is an extremely important piece to be able to do circuits with any measurable depth, for example, that's needed for a lot of the problems that we're interested in solving. So the point here being, these are coming out. We have a long way to go. There's still a lot of work to do and a lot of exploration, but it starts giving some indications that the methods are being developed and the groundwork is being laid to be able to start looking at much more complicated circuits. Okay, so moving over into some of our hardware. So we announced this year Condor, woohoo! We checked off that box. We've been pretty consistent, I think, across the board in terms of checking off the boxes each year at Summit on our roadmap. So we did indeed achieve a 1,121 qubit chip. 50% increase in qubit density and a mile of flex cabling, which is kind of amazing if you think about the density of that packs in. So with Condor, we were really looking at this is what we can do in terms of single chip technology. This is what we can do in a single fridge. That's essentially where we wanted to take it in terms of scaling with those constraints in mind. So we think that essentially we did accomplish this. So Condor unblocked the road to scaling, and now, based on everything that we need to do in order to be able to use quantum computers and to be able to scale well into the future, we need to focus on gate depth and quality of the different qubits. So the other box we checked off in terms of hardware this year that we're very excited about is our Heron chip. So here is Heron. It's been 4 years in the making. So in around 2019 or so, I think the team realized that we needed to go back to the drawing board and take a new approach to some of these chips if we wanted to be able to get to the places that we needed to go to be able to run the circuits that we needed to run. So this has tunable coupler technology. So it's a different architecture. It also has really highly improved things like the gate times are down by they're like a fifth of what they are on our Eagle device. The other thing that I think is probably the most noteworthy change between the Condor chip and the Heron chip is there's no crosstalk at all seen in the Heron chip, whereas that's pretty significant, and you can see it in our Eagle chips, so it has a pretty significant impact. In addition to that, the error rates are much lower. So in some cases, we even get into the 3 nines in terms of error rates of possible using Heron. So we've done a lot of preliminary kind of experiments, like testing out, like rerunning the utility circuit on the Heron, and we see a much improved amount of time that we need to take to be able to run that, and the quality of the results are much better. So that will continue, and I think the team is really excited about trying out Heron for all of their their favorite problems of choice today. So this should play a video of our IBM System 2, which was another one of our announcements. And so the IBM System 2, true to, I think, form, is beautiful, right? I mean, you look at it. By the way, these are actual pictures. So this is not a draw up. It's not CGI. These are actual pictures of IBM Quantum System 2 located in Yorktown Heights. So what's very cool about Quantum System 2 is, first and foremost, it has 3 herons in it. So that's where we're starting with this, is it comes with basically 3 herons. And then to top it off, it's modular. And so it's really built in such a way that we can get to what the vision is of quantum-centric supercomputing, where you can add to it and in whatever way you need to be able to scale out to some very, very large circuit capabilities. So we're very excited about Quantum System 2. We, think that it really is going to help us get to the point where you are now in a regime where you can put the Qiskit and Qiskit runtime, Qiskit 1.0, together with our systems, and really be able to start driving some of the work and research that we all want to be able to do, and that we've all envisioned in terms of thinking about the potential for quantum computing. So Qiskit 1.0 was announced. It has increased performance, stability, and reliability. Again, this is the link to go check out the talk. They go into much more detail there than I will in terms of the specifics of what has actually improved. But I can also tell you that the team is extremely excited about this. With Qiskit 1.0, the other piece that comes with this is that we're talking about it in terms of Qiskit patterns. So basically, it takes any problem and decomposes it into 4 different steps. So in the first step, where you map quantum circuits and operators, some of the improvements in Qiskit 1.0 as you start having the capabilities for dynamic circuits. We've improved our memory requirements as well as a part of Qiskit 1.0 versus other previous versions. In step 2, optimize the problem for quantum execution. So this is really talking about the transpiler and optimizing it for our backends. Something in addition that I'm not going to have as much time to go into, but was mentioned on the first slide, is that we've also incorporated AI here. So there is an alpha version of being able to use AI to help you optimize your code, and also take advantage of the transpiler working hand in hand with Qiskit. So that's something that's not necessarily a part of Qiskit 1.0, but it's in its alpha version, and people can go check it out. Step 3, executing Qiskit runtime primitives with a sampler and estimator. So this has been very much streamlined and simplified in Qiskit 1.0. And then in step 4, which is the post-processing portion of it, we're able to now connect this to things like the serverless pieces that we have in our software. So things like circuit cutting and circuit knitting and entanglement forging and things of that nature. It can directly pipe into that. So it's really making things a lot easier. The whole idea here is that we're getting to a place where we no longer, you don't necessarily need to know what's under the hood in order to be able to run something of interest and get out of an answer in whichever format that you're looking for that is meaningful for you and your work. Okay, so the next piece of this, quantum computing at scale delivered via error correction. So we published another paper. So the first one was the utility paper that I think it got a lot of press. It was on Twitter, and people were talking about it, a lot of buzz. This paper was not as it was probably more quiet. If that makes sense. But basically, this was a paper that was put out on LDPC codes. And what we basically were able to then view in this, and when we looked at the roadmap, thinking about what impact this would have on that, is it gave us a sense of what kind of error-correcting codes we might use and what we wanted to design our architecture in order to be able to implement. So in this particular instance, it has the same level of protection as surface code. It has 6-qubit connections, and then it requires long-range connectivity. But this was something that we viewed as being a really good technical challenge for us, and a way to think about how we were going to actually get to a point where, for example, a 100,000 qubit quantum-centric supercomputer would be able to allow us to get to practical fault tolerance, right? And so that basically gave us an idea of extending quantum utility, what we needed to do and what our goals were. So again, the hardware roadmap, YouTube link is there. This is the change. So the old roadmap on the left, we've now expanded it out. You can see that we have very clear landmarks up through 2029 and then to 2033 plus. Some other things that you might notice the change in terms of like what we're showing here. So we're now showing number of gate counts instead of just qubit count as, again, a way to really underscore that we're committed to our quality and being able to execute gates that are of interest and importance to researchers and to industry. And what you can see is we go from 5,000 gates. That's our 100 by 100 challenge that you guys might remember us talking about. So that's still there. We're now just showing it as 5K. And then we go up with Flamingo to 7.5K gates, and then up to 15K gates in 2028. A big step change here, though, that you'll see is that we go from error mitigation to error correction in 2029. This is a big deal. We are basically putting our stake in the sand that we are going to use these LDPC codes, and we will deliver a device that's capable of 100 million gate count with 200 now logical, not physical qubits. So this is going to be a big change. When I talk to the people in our hardware team, they like vibrate when they talk about this, because this is really the quantum computer that a lot of them set out to accomplish within, and they weren't sure when it would happen. And now we're saying by 2029 we're going to have that. And then with Blue Jay in 2033 plus, we're now talking about 1 billion gate counts and 2,000 logical qubits. So this is now in an area where we really do think that we are going to have the potential to look at problems that we never have been able to look at before. How much time do I have? Oh, man. Okay. All right. I am just going to, okay, there's an innovation roadmap that goes along with this. If you look, at this, it looks like we're sitting still while all these things are, it's like, okay. But actually, there's a lot of work going on underneath the hood. M couplers, L couplers, C couplers. The C couplers are really important for on the chip to be able to implement the LDPC code. So we basically said that between that and then working on the software for the error correction decoder, we're pushing out Kookaburra. We're hoping you give us the grace of an extra year to be able to combine that all together as we're pushing our way out towards Starling. And I'm not, I think, going to have time to talk through all of the technical working groups, but I wanted to mention them because all of this depends, all of these innovations depends on bringing together a number of perspectives from different backgrounds, and we need to be able to stitch together classical plus quantum plus industrial perspectives in order to identify and then go after the challenges that we are most pressing today. So this is a YouTube talk. I hosted a panel at the summit where we got into some details for high energy physics, healthcare, life sciences, optimization, and materials, what really needs to be done there. And each one of these is different, unique, distinct, has its own challenges associated with it. Oh man, I wish I had time to go through this. Okay, there are some papers. So here's our HCLS paper, perspective article, posted online this year. This is for high energy physics. In optimization, we have a GitHub repo on benchmarking, which for optimization, again, it makes sense in this particular instance because there's a lot of focus on different benchmarks here. And then we just published a paper, literally, I think it came out yesterday, on the optimization perspective. And then our materials paper should be coming out, they promised me, next week. They promised me. So be on the lookout for that. We also have one coming in sustainability between materials and optimization. If you're interested, There's a form here, an Airtable, if you're interested in joining, participating, hearing more. Please fill out that form. We'll send you more information. And I'm so sorry for my -5 minutes. But with that, I thank you for your attention.